All right, so let's go ahead and finish up this chapter. We will finish this up with basically looking at some periodic trends. So this will help you in terms of being able to predict the properties of an atom without really having a whole lot of prior knowledge about it. And one of the most important steps in this, or in my opinion, the most important thing in understanding these trends is this slide. Well, this concept, I should say. And that is the effective nuclear charge, also known as Z effective. Okay. So what this is it's the pull or force an electron feels from the nucleus, in other words, from the protons. So we know that the nucleus has positive and neutral particles inside of it. So that positive charge pulls, of course, on the negative charges of the electrons. And we call this degree or this force of pull Z effective. Okay, so the effective nuclear charge. So the closer electrons are to the nucleus, the greater pull they have on the electrons. So in other words, if the magnets are closer, like if you hold two magnets close, they'll kind of start to jump towards each other. That's what we're talking about here. So the closer the charges are to each other, or in other words, the closer the electrons are to the positive charge of the nucleus, the more pull they feel. That's kind of hard to say. So the greater the Z effective, the more tightly the electrons are held, and the more energy is needed to remove the electrons. So the electrons located farthest away in the valence shell have the least experience of Z effective. So the further we are away, the less pull those protons have on the electrons. So that's one reason why when we talk about doing things like making ions, we talk about this happening in the valence shell. And we talk about bonding and all this kind of thing. It's all happening out in the valence shell. Okay, so that's where Z effective is the weakest. Okay, so Z effective explains the reason behind the periodic properties and trends of the elements. And the general trend of Z effective is it increases going across a period and decreases going down a column. So another way to look at it as I like to think of this in terms of increases and increases. So what they're saying is it increases going across the period, so left to right increases. And they say decreases going down, but I think it's easier to think about it in terms like this. Okay, so towards fluorine. So increases and increases. I think this is the best way to remember it. So if you remember that fluorine has one of the strongest Z effectives on the periodic table, and you remember that moving left to right it increases, and moving bottom to top it increases, I think that will make your life much easier than trying to remember it in both directions. Okay, so just remember, as you move towards fluorine, the pull of the nucleus on the electrons increases. Okay, and the main reason for this is how effective the other electrons are at shielding those outer electrons. So it increases across the period owing to the incomplete shielding by the inner electrons in atomic orbitals, in other words, in the subshells. And so in terms of shielding ability, S is better than P, which is better than D, which is better than F. Okay, so our S orbitals are relatively good at shielding, but as we start to move out, we get less and less shielding. And if you remember the shapes of these orbitals, that probably starts to make sense, right? So there's gaps in these. You could kind of think of it that way. That's not everything, but that's part of it for sure. And if we want to calculate Z effective, we can say the atomic number minus the inner electrons will be equal to Z effective. Okay, so the pull felt by the 2s electrons in lithium will be equal to 3 minus 2, which gives us 1. And you can basically, that gives you a way of comparing if you would like to do that. Okay, and this is essentially a plot of the actual orbitals themselves and sort of how much radial probability, meaning kind of gives you an idea how much shielding they have. You don't really have to look at this if it confuses you. But it just kind of shows you that some types of orbitals, some shapes of orbitals, are more effective at shielding the outer electrons than others. Okay, so some general trends here. Okay, so notice, again, so we're moving kind of thinking in our minds about this upper right-hand corner. Okay, so one thing to think about is this purple arrow, electron affinity. Okay, so I'm going to write in fluorine here because it's a good one to keep in mind. So when we're talking about Z effective, another way of thinking about this is electron affinity. Okay, so sort of how hungry is an atom for electrons. A lot of that kind of coincides with Z effective. Not exactly, okay, but you can kind of think about it in this way. Okay, and so if we think about fluorine as being sort of the hungriest atom, so to speak, okay, then these trends will sort of start to make sense. Okay, so as we move up and right in the periodic table, we have increased electron affinity. Okay, we also have increased Z effective, if you remember. Okay, so now if we start to look at some of these other trends, so atomic radius goes up as we move down and to the left. In other words, as we move away from fluorine, so down and left, okay, our atomic radius increases. Why? Because we're getting less Z effective. Okay, electronegativity increases as we move towards fluorine, and ionization energy increases as we move towards fluorine. So essentially, the more hungry that atom is to keep those electrons, okay, the more difficult it is to start to remove them. Okay. And then we see that metallic character increases left, so down and left, and non-metallic character increases up and right. Okay. And we'll kind of look at some of these. So this one, the radius. Okay, so the size of the electron, size of the atom increases going down a group to the decrease in Z effective. So increasing radius going from top to bottom, and decreasing radius going from left to right. So another way to look at it is that our biggest atoms will be down and left. Okay, so increasing as we move down, decreasing left to right, or you could think of it as increasing from right to left, however works for you. And notice there are some abnormalities in here, so it's not just purely these trends, but it gives you a general idea. Okay, so you can kind of see by their heights that it's not exactly 100% accurate to say that this atom will for sure be bigger than that one. Not necessarily, but you see that the general trend is there. Okay, and the size increases going across a period due to increasing Z effective. So we know that moving left to right, we're increasing our Z effective, so the pull of those electrons gets stronger, and as we move down, it's getting weaker. Okay, so the atoms get bigger. So if we have stronger Z effective, we have smaller atoms. If we have less Z effective, we have bigger atoms. And this just sort of puts those trends on a plot for you. I'm going to skip over this. You can look at this if you're this kind of person. Otherwise, it may confuse you. So I'm going to keep moving. Okay, so here we want to know which one has the largest atomic radius. Okay, this shouldn't be too difficult based on what you just learned. So pause me and give these a try, and then we will go over them together. Okay, so let's take a look at these. So it just wants to say which has the larger atomic radius. So the first one, we're comparing nitrogen and fluorine. So take a look at your periodic table. And of course we know fluorine is in that top right-hand corner. So we said that's where the most Z effective is. Okay, so nitrogen will have a bigger radius since it has smaller Z effective. Okay, next one, carbon versus gallium or germanium. Yeah, germanium. Okay, so which of these? So look at your periodic table. You see carbon is above germanium. Okay, so what did we say our trend was? So Z effective is higher going up and right. So if we're below something in a column, of course, germanium will be larger since it's further down. Next one, boron and aluminum. Again, aluminum is below boron, so aluminum will be larger. And the last one, lithium and potassium. So lithium or potassium is below lithium. Lithium is above potassium. They're sent in the same column. Okay, so lithium or potassium. maybe make sure I said that right. So lithium is above potassium. Yeah. Okay, so potassium will be larger. Okay, since it's more in that bottom left corner. Okay. So what about if we're talking about cations now? So this is when we start to remove electrons. So one thing we can say is that cations are smaller than the atoms from which they come. Okay, so if we remove electrons, the electron-proton attraction is increased. Okay, so overall the size decreases. So they sort of start to shrink. So as you pull things away, we start to shrink the atom. And that should hopefully make, relative intuitive sense. So if you're pulling things off the atom, it's going to start to decrease in size. So just taking a look at this. So in every case, so first one here, just lithium. This is the first column is group 1A, so group 1. So you see lithium versus the lithium ion, sodium versus sodium ion, potassium versus potassium ion. And this is true all across the board here. So you see beryllium, magnesium, calcium, all these guys. So one thing hopefully you're noticing is that in every case, the cation is significantly smaller, and these numbers in the bottom are in picometers, so they're atomic radii in picometers. In every case, the atomic radius is smaller, so they are significantly smaller in size compared to their parent. Okay, so the cation, the positive charged ion, is always smaller. Okay, so that's really all you need to remember if you're comparing, something's native state or its cationic state. The cationic state is always going to be smaller, and hopefully that makes sense since we're removing something from the atom. Okay, and the opposite is true for anions. Okay, so we go from a regular, say, fluorine to fluoride ion. Okay, the atom is going to grow. So anions are larger than the atoms from which they come. And now with the electron-proton attraction has decreased, so the size increases. And hopefully, again, this makes sort of intuitive sense. If you're adding to the atom, it's going to grow. Okay, and here we have the same situation where we have here group 6A, group 7A, where we have oxygen, and then oxygen 2 minus, fluorine and fluoride. And what you see in every case across the board is that if we start to add electrons to these parent atoms, okay, so we form anions out of them, in every way, or in every case, the atomic radius grows larger. Okay, so this problem wants you to say which has the larger radius, and you have some anions, you have some cations. So just compare these and see what you come up with. Okay, so let's compare these. The first one we have sulfur versus sulfide. Okay, so we have a parent versus the anion. So we know the anion will always be larger. Okay, so we've increased the number of electrons, so we've decreased the effective pull on the electrons, so to speak. So of course the anion will be larger. The next one, we have calcium versus calcium cation. Okay, remember we said if we pull electrons away, we increase the proton's force, or increase the pull of the protons on those outer electrons. And generally speaking, we're just taking things away. Okay, so of course calcium will be larger, or the parent will be larger. Okay, and the last one we have bromine ion versus krypton noble gas. Okay, so we have a note here. So for isoelectronic species, the more negative the charge, the larger the atom or ion. Okay, so in other words, what it's saying is the bromide ion is still going to be larger even though they have the same number of electrons. So bromine still has fewer protons since it's still bromine, but now it has a negative charge, so it's still going to be larger. So if you see things that have the same number of protons but one has more electrons, you're still going to have, or if they have the same number of electrons, let me say this correctly, if they have same number of electrons, but one has one fewer proton, the one with the fewer proton will be larger. Okay, so in other words, the anion will be larger. Okay, so next one, ionization energy. So this is the energy required to move an electron from an atom in the gas phase. So the first ionization energy increases across the period because we know that Z effective increases as a result of poor shielding. So again, since Z effective increases, ionization energy increases. So you can think of ionization energy as how hard is an atom holding on to that electron? How hard is it to take it away? Okay, then it decreases going down the column because the atomic size also decreases. Oh, I'm sorry, because of the increase in atomic size and decrease in Z effective. Okay, so since Z effective goes down as we go down a column, ionization energy does as well. Okay, so this is why metals lose electrons more easily, and they also have lower first ionization energy. Okay, nonmetals lose electrons with difficulty, and they have higher first ionization energy. Okay, so just putting that in sort of a graphical form. Okay, so down in the bottom right here, as we go down a column, we have decreasing ionization energy. As we move left to right, increasing. So in other words, generally speaking, in this direction, you have increasing first ionization energy. So if you remember, this is what I was saying, if you remember your Z effective rules, even if you forget some of these, you can kind of work them out. And I honestly think that's the better way to go, is to really, really try to understand what's causing these to happen and not necessarily just memorize the trends. If that thing you think just memorizing is better for you, that's nothing really wrong with that. But understanding Z effective, and then you can understand all the rest right along with it. Okay. So here we just want to choose which has the first higher first ionization energy. So take a couple seconds, answer this one, and then we'll go over it together. Okay, so let's take a look at this one. So again, we're looking for the highest first ionization energy. So we want to compare aluminum to sulfur. So we have to find them on our periodic table. And we see aluminum is to the left of sulfur. And remember, ionization energy increases left to right. So of course, sulfur. The next one, arsenic and antimony. Okay, so if we look at our periodic table, we have to find arsenic, we have to find antimony. Okay, antimony is below arsenic, and remember we said it decreases as we go down. Okay, so of course, arsenic. Next one, nitrogen and silicon. Okay, so find them on your periodic table. We see silicon is left and down from nitrogen, so of course nitrogen will have the higher first ionization energy. Okay, so hopefully these are clicking for you and you're not struggling too much. If you do, let me know and I can try to help you out with these. Okay, so general trends in electron affinity. Electron affinity is the change in energy, so delta E, involved when an atom gains one electron to form an anion. Okay, so it can either be endothermic or exothermic in nature. Okay, and it's a result of electron-electron repulsion within orbitals and the volume of the atom. So general trends. Electron affinity increases across a period, so left to right, increases as a result of the increase in Z effective. Okay, it decreases going down as a result of a decrease in Z effective. So I prefer to think of electron affinity as, again, how hungry is the atom. That's not exactly right, but it works. Okay, so it's very similar to ionization energy. It's very similar to Z effective. All these things sort of follow the same trend. But you have to kind of keep what they are straight in your mind, but understanding the trends can be made easy in that way. Okay, so electron affinity is the willingness to accept electrons into the valence shell. Again, it's sort of how hungry is it. Okay, the fluoride ion has a lower electron affinity than the chloride ion because it has a smaller volume and greater E, in other words, electron-electron repulsion, than chloride. So electron affinity is the greatest for halogens. Electron affinity is greater for nonmetals than for metals. In this, where they're comparing fluoride and chlorine, again, this is because of fluorine's small size. Okay, so this is why you would maybe expect hydrofluoric acid to be the strongest acid, but that's not exactly true. Okay, and this is one of the reasons why. Anyway, so a larger electron affinity value means a very stable ion. So larger electron affinity is more negative energy, which is more stable. So in other words, when we think about an energy scale, the more negative it is, the more stable it is. Okay, just for example, so first and second electron affinities for oxygen, for instance. Okay, so we have oxygen. Okay, so we're going to add one electron. Okay, so we're going from O to O minus. Okay, so it says delta E for the first electron affinity is exothermic because oxygen has the affinity for an electron. Okay, which might sound kind of confusing, but what they're saying here is that the energy goes down. Okay, so it has affinity for the electron, so it goes down in energy. That's why it's exothermic. Okay, the second one, when we add another electron on, okay, so delta E for the second EA is endothermic because of the increase in electron-electron repulsion. Okay, so the first one, in other words, it's easy to add the first extra electron. It's more difficult to add the second one. It's kind of what they're trying to say there. Okay, so I think this is the last trend here. So just properties of metals and nonmetals. So the characteristics of metallic elements. We know they're malleable and ductile, which means they can be molded and they can also be stretched into wires. We know they're shiny. We know they conduct heat and electricity. Most oxides are basic and ionic, and they generally form cations in solution, and they lose electrons in reactions. And so what they're saying is generally the metal is the one being oxidized. Okay, the characteristics of non-metallic elements, they're brittle. Okay, so they're dull, non-reflective, generally speaking. They're generally good insulators. Most oxides are acidic and molecular versus ionic. And they form anions, and they also are a big part of polyatomic ions. And they tend to gain electrons during reactions, so they're reduced, generally speaking. Okay, and generally speaking, metallic character decreases as you move left to right and increases as you move top to bottom. So decreases left to right, increases top to bottom. Okay, the metallic character of an element is about how closely its properties match the ideal properties of a metal. And remember that metals are the most malleable and ductile, better conductors, and easier to ionize. Metallic character decreases from left to right across the period. So metals are found at the left of the period, and nonmetals are found to the right, of course. So we know like our main group, our left-hand side main group is metals, and our transition metals are over on the left. Okay, and like our halogens and gases are over on the right. And then we know metallic character increases down the column. We know that nonmetals are found at the top of the middle main group elements, and metals are found at the bottom. Okay, so just basically trends in metallic character, increases from top to bottom, decreases from left to right. So if we're over on the left-hand side of the periodic table or in the transition area, you know you're going to have more metallic character compared to if you're over in the nonmetals and metalloids and gases. Okay, so that is the end of the chapter. Hopefully you liked that I broke it up into those two sections. I think it made a lot of sense. Okay, so that will be it for today.